Hello everyone, can you hear me?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
So we will just wait for 3-4 minutes and then we will start. Hello everyone, can you see the screen which I have shared?
Yes, sir.
Yes, sir.
Okay, so this course is CLL251 heat transfer. Again, mostly I used to take this course on a blackboard earlier, but this time I thought I can, cover it on PowerPoint, because this is a curtailed semester, isn't it? We will have only a 36 lectures. So it is better to conduct it on PowerPoint. So that is the reason why I am doing it on the PowerPoint for the first time. So this is the third time I'm taking the course, but first time on PowerPoint. Okay. Anyway, so in this particular course, the reference textbook is Heat Transfer by BK Datta. This book is easily available on Amazon. You can buy it from the Amazon. I think it will cost you around 300 or 400 rupees, not more than that. It is not costlier book. So you can purchase it from Amazon, or if you wanted to get a e-copy, whatever you wanted to do, that is up to you. But everything will be covered from the book Heat Transfer by BK Datta. In fact, all your examinations will be open book, and the book referred will be BK Datta. Okay, so let us look at the course strategy before we start today's class. So again, this is a heat transfer for chemical engineers. Name of this course is heat transfer for chemical engineers. CLL251 is the code. Credit is 3. Again, uh, we are going to have minor 1. So the weightage to minor 1 will be 30 marks. Then we will have 2 quizzes. Again, these quizzes will be similar to the minor 1, but among these 2 quizzes, only one is compulsory. So that means what? Best one from of these 2 will be considered for your marks. So 30 marks each will be given for each quiz, and whatever the best marks you have obtained, that will be considered. Okay. Again, one more point to note down here is, if you miss both the quizzes, then you lose all 30 marks. There will not be any re-quiz like a re-minor or re-major. There will not be a re-quiz. Remember, here we are having 2 quizzes. That means you have a choice of missing one. You can miss one quiz if you wanted to. If you wanted to give both, it's perfectly all right. But there will not be any re-quiz. If you miss, you miss.
Excuse me, sir.
Yes,
So
please
the
go ahead.
course is for 3 credits or 4 credits? Actually, on e-academics it was mentioned that the course is for 4 credits.
Okay, let me check. Let me check. I have not checked. I think I will check it whether it is 3 credit or 4 credit. Okay.
Thank you.
Exams will be objective type.
Exams will be. Let me go to the exams first. Let me just cover this part first, and then we will go to the exams. So again, see, these quizzes will be similar to the minor one. It will not be objective. This will be, you will have to solve the problems. You will have to write the answers based on that. Okay. Again, all the examinations and quizzes, these will be done on Moodle. So this will be auto graded by the Moodle. Okay. All examinations will be conducted on the Moodle. Again, mostly the questions will be connected questions. It will not be independent questions will not be there. So connected questions will be there on Moodle and auto graded by the Moodle. So everything will be done by the Moodle. Okay. No answers will be accepted by emails. I am telling this upfront in the first class itself. Okay. If you have any internet problem in between in the minor or major, you will have to write re-minor or re-major. There will not be, your answers will not be graded if you submit it by email. Okay. So the answers have to be submitted only on Moodle, and Moodle will do the auto grading. Everything will be done by the Moodle. Remember, in this course, there are 220 students. It is really difficult for me to check the individual copies on screen. So it is better to have the examinations done on Moodle. Okay.
Excuse me, sir.
Yes, please go ahead.
So the examinations would be objective.
No. Examinations will not be objectives. Will be you will have to write the answers.
So there'll be numerical types, sir, because
Numerical
if they are
types,
being
yes,
auto-graded,
yes.
so in that case, it can't be.
Yes. All the questions will be numerical type, no objective type questions.
Okay, sir. Thank you.
Okay.
Got it, sir.
The another point is classes and tutorials will be conducted online on MS Teams. The way we are doing today's class, all the classes and the tutorials will be conducted on MS Teams. So mostly the classes I am going to record. Okay. So for example, you can see today's class I have started the recording, isn't it? So all the classes will be recorded, but tutorials will not be recorded unless some in some emergency situations I may record the tutorials also, but as of now only the classes will be recorded, tutorials will not be recorded, and you will have to attend all the tutorials seriously to understand how things are done. Okay. Because the point is tutorials are in order to make students understand the details of the course, isn't it? So that is why I feel tutorials should not be recorded, and I want all the students to attend the tutorial seriously. Attendance is not compulsory as such, but see, it is not, I cannot make it mandatory, but I want definitely most of you to attend on, uh, around 75% classes. If more, it's perfectly all right and good. Less than that, probably you will miss many things. Okay. Again, grading will be relative. So don't later on say that please give me a grade based on whatever the set limits you have in your mind. Okay. So grading is relative. If you score less, probably you will get a very good grade with less marks. If you score more, then in relative grading you may get a slightly inferior grade based on the marks obtained. Okay. So it depends on how your friends have scored. The last point is audit pass grade. So remember, in this semester you can have a choice of auditing one core course, isn't it? So audit pass grade is 30 marks and above. So if you pass this course, see, remember 30 marks is the pass limit, isn't it? So if you get 30 or more, then you get the audit pass grade. Okay. Again, see, whenever we are doing the classes, all these recording remains on the MS Teams only for 20 days. Okay, so all the classes which are recorded on the MS Teams, you can have those links only up to 20 days. So it is your responsibility to download it from the MS Teams. I will not upload it on Moodle. Nothing will be uploaded on Moodle, anything. Only the tutorial sheets will be uploaded on MS Teams, not on the Moodle. Okay, so everything will be on MS Teams. Only the exams will be conducted on Moodle. Okay, so it is students' responsibility to download the recorded lectures regularly in a given time frame. If they miss this window of 20 days, then they will have to arrange it from their friends. I am not going to send a video to each student independently. Okay, so these video links will be available only for 20 days. It is your responsibility to download it. Okay. Again, only these videos will be given. Don't ask for the PowerPoint presentation later on. All these PowerPoint presentations which I am going to use, anyway, I am going to follow only these PowerPoint presentations in the videos. So videos will be available. These separate PowerPoint presentations will not be available. Okay. So syllabus for this course, syllabus is again straightforward. We will start with steady state, unsteady state conduction. Then we'll move to heat transfer coefficient, concept of heat transfer coefficient. Then we will look at forced convection, free convection, nucleation and boiling, radiation, heat exchangers and evaporators. So all these topics are covered in the book which I have already mentioned. So book we are going to follow is Heat Transfer by B.K. Datta. Again, one more important point to note down. This is based on the experience. whenever the exam papers are given to the student, they search on Google some correlations, and whatever the correlation is available on the Google, they use that correlation in their solution, and later on they argue that I have used the correct correlation. Okay. The point is, in examination, the correlations only from this book, Heat Transfer by BK Datta, will be allowed. If you download any correlation from any XYZ book or any random internet source, that will not be considered, because there is, see, in heat transfer, based on the change in the correlation, your answer can vary by 10%. Then you can argue that please increase the tolerance limit, because I have used some other correlations. Now my answer is also correct. So this type of arguments will not be considered later on. You will have to use only the correlations given in a textbook Heat Transfer by BK Datta. Okay. If any other correlations are required, I will give it in the problems, or I will mention it clearly. Other than that, you will not use the correlations by on your own from some random internet source. Okay. So this is the course strategy. If you have any doubt, any questions till this point, please let me know.
So there's only one small doubt regarding the PPTs. That, sir, at times a lot of students do not have sufficient internet to download the videos. So
Okay.
if possible, could you please,
So that
attach
is
the
why,
PPT?
see, all this material is taken from the book Heat Transfer by BK Datta. You follow the book directly. So nothing is outside from this book. In that case, you follow the book.
So, but just directly referring what you taught
That is
while the
what I'm
PPTs
saying.
would
That
be.
is what I'm saying. So see, the point is, I want students to go through the details given in the book. In the PPTs, we generally do not have a sufficient detail. We only have a bullet points. I don't want you to remember the bullet points. Okay. I want you to go through the details of the each topic. So that is why I am telling you upfront that the book which I am going to follow is Heat Transfer by BK Datta. This is not a costlier book. You can purchase it. It's only 300 or maximum 300 to 400 rupees. Okay, it is available online also. You can get the online copies also. You can download it also if you know how to download it. So it is available. It is available. Okay, this book is available.
Fair, sir. We'll download the videos and refer the book as well.
Yes.
And sir, how about the tutorial recordings? Because we need it for
Tutorials
last
will
minute
not
revision.
be recorded unless some emergency situations are there. Only in that case the tutorials are recorded, because in tutorials probably I am going to use the blackboard. So we are going to solve the problems directly on the blackboard, and therefore I want all the students to present there. Okay, so your active presence is required. So tutorials mostly will not be recorded unless some emergency situations are there. Okay. Is it okay?
Yes, sir. So we'll try our best to come up in very good numbers, but it'll be very nice if you could please record the tutorials as well. Like at times there are internet issues and all that, so
Okay,
we are not able to
I
attend.
take your point positively. Let me just see. Probably I will, record the tutorials as well. No problem. Okay,
Thank you so much,
fair
sir.
enough.
It'll be really nice of you.
Again, another point is, uh, okay. Okay, so let us start with the course, unless you have any other point to discuss. Is there any more point to discuss, or we can start?
Sir, how about the tutorial timings? The slot that we'll be having for the tutorials?
Tutorials, we will have tutorial timing is from 1 to 2 if I'm not wrong. Isn't it? Let me just check the timing of the tutorial. Let me just check.
Yes,
So
sir. We'll have to coordinate with other professors too for the same.
why? Because in other courses, the tutorial timing is not fixed.
Right. So actually tutorial timings are decided by the professors, so we try to adjust it amongst ourselves with the professors.
So can you suggest me the timing for the tutorial? The tutorial timing given in my schedule is 1 to 2.
Sir, on what days do you plan to take it for different groups?
It is Monday is T3, Tuesday T4, Thursday T1 and Friday T2.
Sure, sir. We'll let know the other professors in that case that you fix the slot 1 to 2 on these 4 days.
Other options could be, instead of having the tutorials in 4 different batches, I can have it like a class also. So please let me know if that is okay, or you want to have a tutorial individually for each group. It's perfectly all right for me.
So in most of the classes or in most of the courses from the previous semester as well, what we've had is that we've merged two groups together and we've had a couple of tutorials in the week.
That is
Instead of
also
course.
fine with me. That is also fine with me. So can you tell me, how to go ahead with this? Because today we have to do the tutorial then.
Sir, in general, like in the previous semester, we had CLL110, which had group 1 and 2 and 3 and 4 merged. Whereas today, Professor Gaurav Goyal has said that he'll be merging group 1 and 3 and 2 and 4 for tutorials.
Okay, so we will also follow the same strategy. 1 and 2 we can merge, and 3 and 4 we can merge. It's okay.
So 1 and 3, 2 and 4 for this semester.
1 and
1
3
and
and 2
3?
and 4. Yes. And we can have it 1 and 3. We can have it, let's say, on Monday.
Okay, sir.
And 3 and 4 we can have it on Thursday.
Okay, sir. We let the entire batch know about this. 1 and 3 on Monday and 2 and 4 on Thursday. 1 to 2.
Yes.
Thank you so much, sir.
So 1 to 2 is the timing given. So we will stick to that time. I think there should not be any problem. Okay.
Yes, sir. Yes, sir. Thank you, sir.
Okay. So let us start with the course. So as the name of the course is heat transfer. Okay. So if you look at the processes, the heating or cooling of materials is an indispensable part of processing, production, fabrication, or shop floor jobs in engineering practice. So this is a general statement. You can clearly see that in any process industry, the heating and cooling is the commonly present operations, isn't it? Correct. So therefore it is important to study the heat transfer in order to minimize the loss or gain of heat during the process in order to operate a process in a most economic way possible. Okay, so what I wanted to say here is, since most of the process applications there is always a heating or cooling of the process takes place, and this is directly related with how much energy is utilized in the process, isn't it? And therefore, minimizing the loss or minimizing the gain of heat in the process is extremely important, because that will lead to the minimization of the energy required, and that will lead to the economic way of operating the process. Okay, so let us take a very simple example. So this is catalytic air oxidation of ammonia to produce nitric acid. So this particular flow sheet you can see here.
So your screen is not visible right now, I guess.
My screen is not visible. Okay,
Yes, sir.
let
It's
me
not
just
shared.
share.
Yes, sir.
Is it visible now?
Yes, sir. It is.
Okay. Okay. So what we were discussing here is in all the processes, in all the chemical processes, you can see the heating and cooling is the indispensable part. And since heating and cooling is related with how much energy is supplied to the process, study of heat transfer is extremely important, because that enables you to operate your process in a most economic way. So by minimizing the energy gain, the heat loss or the heat gain in the process has direct implication on how much energy is required. Okay, so let's take a simple example to understand the requirement or the importance of the heat transfer. So this particular flow sheet is nothing but the catalytic air oxidation of ammonia to produce the nitric acid. Okay, so how the nitric acid is produced? In general, the ammonia is stored at atmospheric pressure and around -33 degrees Celsius in a storage, in a cylindrical, in a storage. Okay, so clearly the ammonia is stored in a liquid state. So that it is stored in a liquid state because that facilitated a better storage. So this storage facility always have to have a refrigerating unit which will maintain the temperature around -33°C. Okay, so the refrigeration part is required when we look at the storage of the ammonia. So water and air that can be taken at the ambient temperatures. So how the nitric acid produced? So first, the ammonia which is stored in the storage at -33°C in a liquid state is vaporized in a vaporizer. So in a vaporizer, the steam is used to vaporize the ammonia to a vapor state, gaseous state. Then this gaseous ammonia is then mixed with the compressed air, and this mixture of the compressed air and the ammonia is then fed to the reactor. Okay, again, the air is taken from the ambient. Air is compressed in a multi-stage compressor. So during the compression, again the temperature of the air increases. So in general, two-stage compressor is used. Again, uh, the heat generated in this compression process is used for heating the tail gas coming out from the absorption tower. So heat is exchanged with the tail gas coming out from the absorption tower, and this tail gas is then given to the tail gas preheater. Okay, so this cooled compressed air is then mixed with ammonia, and this mixture is then fed to the reactor, and in the reactor the reaction temperature increases up to 800°C. So this reactor is also associated with waste heat boiler, so which utilizes the uh, high temperature outlet gas coming out from the reactor, and uh, uh, this exchanges heat with the boiling water to produce the steam. Okay, so the waste heat boiler is associated with the reactor that I have not shown separately here. So that is the part of the reactor itself. So the reacted gas which is coming out from the reactor at 800°C exchanges heat with the boiler boiling water, and the temperature of the exit gas decreases around 275°C. So 275°C. So the outlet stream coming out from the reactor plus waste heat boiler is around 275°C. So this temperature is still too high. So this outlet gaseous stream then again exchanges heat with the tail gas, and this heated tail gas is then supplied to the tail gas turbine. So tail gas turbine produces the power, and that is used for running the multi-stage compressor. Again, the cooled gas, the cooled reaction mixture is then given as an input to the economizer. In the economizer, again the heat is recovered from the outlet stream, and this outlet stream from the economizer is then again exchanges with the boiler feed water, and further the outlet stream from this, the second heat exchanger, is given to the condenser, where again the temperature is reduced by condensing vapor here, and this cooled gas is then fed to the absorption tower where it contacts with the water to produce the nitric acid. So here the reaction scheme is ammonia reacts with uh, oxygen to produce the oxides of nitrogen, and these oxides of nitrogen then reacts with water to produce the nitric acid. So this is the reaction scheme. So here you can see we start with the refrigeration, then there is a very high temperature is generated in the reaction, and this the heat generated is recovered through the preheater, economizer, and heat exchangers. So clearly here you can see a simpler process of nitric acid production also have so much heat transfer units associated with, isn't it? So clearly the heat transfer is extremely important in the process applications. Okay, is there any question?
No, sir.
Okay, So let's move to the next slide. Okay. So similar to the nitric acid production process, there are several processes. I have listed some of these here. In a power plant, you can have a rating boilers, high rating boilers, in which the heat transfer occurs from the hot combustion gases as well as from the white hot refractory furnace walls to water boiling inside an array of tubes. The steam leaving the turbine is condensed on the huge surface condenser. So here you can see not only the heat transfer is taking place, the heat transfer is taking place with the phase change. Okay. Again, the another example could be in the hot rolling mill of an integrated steel plant. Large metal blocks are shaped into sheets, which are then cooled by the flow of water. Okay. Similar to these, even in the nuclear power plant, you can see a complex, heat transfer, process is occurring. Okay, so these are the numerous examples which are there in the process industry, and based on this, we can clearly conclude that heat transfer is extremely important for the process engineers or for chemical engineering. Okay. Okay. So now what is heat transfer? Again, I am going through the basics. I'm sure you all have gone through these details in your JE days, but just for sake of continuity, I'm still going through these details again. Okay. So heat transfer is the transport of the heat energy from one point in a medium to another in the presence of a temperature gradient or a temperature difference. So whenever there is a temperature difference or a temperature gradient, the heat is transferred from the high temperature to the low temperature. Again, what is the driving force for the heat transfer? The driving force for the heat transfer is the temperature difference between the 2 points in the same medium or between the two different mediums when they are in a thermal contact. Why heat transfer is important to study? Heat transfer is important to study because not only it gives the mechanism of the transport of the heat energy in various practical situations, but also it helps us in designing or sizing or improving the design of the equipments. So by studying the heat transfer, you can be able to design your equipments in a much better or economic manner. Okay. If we look at the difference between heat transfer and thermodynamics, uh, the basic difference between the heat transfer and thermodynamics is heat transfer looks at the speed of the heat transfer. Okay, so it looks at the kinetics probably, whereas thermodynamics looks at the extent of the heat transfer. So whether the heat will be transferred or not, that type of questions will be answered by thermodynamics, but how fast the heat will be transferred, this type of questions will be answered by heat transfer. Okay, again, heat transfer gives the rate of heat transfer, whereas thermodynamics will only give you how much heat will be transferred if equilibrium shifts from one place to another, how much maximum heat transfer will be there. Okay, so that limit or the possibilities will be given by thermodynamics, whereas the rate or uh, uh, the speed of the heat transfer, that will be given by the heat transfer. So there is a small difference between heat transfer and thermodynamics. Okay. Again, what are the different modes of heat transfer? So this anyway you all have gone through earlier in your when you have studied for JE, but still I'm going through the details for the sake of continuity. So modes of the heat transfer. So there are three modes of heat transfer: conduction, convection, and radiation. So out of these three modes, the most commonly present modes are the conduction and convection. Whereas when the temperature is very high, in such cases, the prominent mode is the radiation. Okay. Now let's look at the details of each of these modes. So uh, conduction heat transfer is an atomic or a molecular process. So it is similar to diffusion. Conduction is similar to diffusion. So it occurs at a molecular or atomic level. It occurs in the presence of temperature difference and is not accompanied by an macroscopic or bulk motion in the medium. So this is very important. So conduction is the mode of heat transfer which is without any macroscopic or a bulk motion in the medium. Okay, so only microscopic movement of electron or vibration of the lattice, these are the things which takes place in the conduction. Okay. So conduction is the only mode of heat transfer in the solid medium. So when we are looking at the solid medium, conduction is the only mode. It may also occurs in stagnant liquid or gaseous medium, but prominently for liquid and gases, the most governing mode of heat transfer is convection. But even if we look at the convection at the molecular level, the heat is transferred only by the conduction only. Okay, so at a molecular level, the heat is transferred only by conduction. Okay, so again, it is similar to the diffusion and is governed by the Fourier's law of heat conduction. So we will see this Fourier's law of heat conduction in detail in subsequent slide. So if you look at the conduction, let's look at this particular figure. Here you can see if left hand side the temperature is, let's say, 25 degrees Celsius, and on the right hand side of this slab the temperature is, let's say, 500 degrees Celsius. So heat is transferred from this 500 degrees Celsius to 25 degrees Celsius and via the movement of the electrons. If we are looking at the metals, if we are looking at the crystals, then it will be based on the vibration of the crystals. Okay, let's look at the another mode, which is the convection. So convection is present whenever there is a velocity field or whenever there is a turbulence presence in the fluid medium. So convection means the transport of heat energy by a way of displacement of fluid element from one point to another point, which is at a different temperature. So this is very important. So unlike the conduction where there is no macroscopic movement of the fluid uh, uh, particles, or there is no macroscopic movement of the fluid elements, in convection there is a movement of the fluid elements is there. So there are convection currents are there. If you let's say if you add a very hot water in a cold water in your glass, you can clearly see there are currents present, isn't it? So all these currents are because of the convection. Okay, so again convection has two types: forced convection and free convection. So this displacement of the fluid, if this is caused by the external unit or the velocity field is generated by external pressure, in that case the convection is referred as forced convection. There is another type which is nothing but free convection or a natural convection. So natural convection occurs whenever the displacement of the fluid it takes place because of the density difference or because of the density gradient. Okay. So the forced convection occurs when the motion in the medium is caused by an external mechanical unit such as pump, blower or agitator, whereas the free or natural convection occurs when motion in the medium is created by an adverse density gradient as a result of temperature difference. So this happens when the temperature of the fluid at a lower level becomes higher than that in the upper level. So you can clearly see in this particular figure, if suppose in the bottom, if we heat this the liquid present in the bottom, let's say if we heat by a external heater, so temperature in near this bottom will be higher than the temperature at the top, and because of that what will happen, the density of the liquid at the bottom is going to become lower than the density of the liquid which is at the top, and because of that the fluid element from the bottom will move from bottom to the top. So there is a movement of the liquid element takes place because of the density difference, and such type of convection is referred as free or a natural convection. Again, unlike the conduction, the governing equation for the convection is a Newton's law of cooling. So what Newton's law of cooling is, the heat flux is proportional to the temperature difference. So that is what the Newton's law of cooling is. We will see the details of these laws in subsequent slides. Okay. So unlike this conduction and convection, there is another mode which is a radiation. And unlike the conduction and convection, radiation mode do not require a medium for transport of the energy or heat. Okay, so a body of a temperature above absolute zero always emits energy in the form of electromagnetic waves. Okay, so here you can see there is a body at 500 degrees Celsius, there is another body at 100 degrees Celsius. Both are emitting the radiations, and the heat transfer is based on the difference between the heat emitted and heat absorbed. So net heat transfer is calculated here. So here you can see the body A also emits, it also absorbs the heat. In the same manner, the body B also emits the heat and it also absorbs. But since the temperature of the B is 100 degrees Celsius, it is going to absorb more energy because the radiation emitted from the body at 500 degrees Celsius will be higher, and therefore there will be a net heat transfer from the body at 500 degrees Celsius to the body at 100 degrees Celsius. Okay. So the second point here is the rate of release of such. Is there any question? Hello?
No, sir, no questions.
Okay. Okay. So the important point here is the rate of release of such energy is proportional to the fourth power of the absolute temperature of the body. So that is what the Stephen Boltzmann law is. So the energy emitted will be proportional to the fourth power of the absolute temperature. Okay, so clearly the such heat transfer is governed by Stephen Boltzmann law. And this mode is important, becomes important at higher temperatures. So at lower temperatures, conduction and convection is the prominent mode, but at the higher temperature, the radiation is the most important mode of heat transfer. The another concept in radiation is a black body. Okay, so generally all bodies are not equally good emitters or radiation. So a standard or a perfect emitter is referred as a black body, and it acts as a reference with which any other body may be compared in respect of its effectiveness as an emitter. So this property is called as emissivity. So the black body concept is used in the heat transfer. So emissivity of the black body is 1, and based on that all other bodies are compared. Okay, so another important concept which is used in the radiation is a view factor. Okay, so so view factor is nothing but this factor takes into account the fraction of the area of a body which can be seen by another body. So this concept of view factor, emissivity, Stephen Boltzmann law, all these details we will see later on when we will look at the radiation in detail. But this is just for a continuity purpose. I have given some details of the radiation heat transfer here. Okay. So let's move to the conduction, particularly the steady state conduction in one dimension. Unsteady state conduction we will look at later. So conduction of heat means the transport of heat energy in a medium from a region at a high temperature to a region at a lower temperature without any macroscopic motion in the medium. So this is what we have said in the earlier slide. So in conduction, the heat is transferred from high temperature to a lower temperature in a medium without any macroscopic motion in the medium, without any macroscopic motion in the system. Okay, so that is what the conduction is. Now if you look at the conduction in the solids, so heat conduction is due to vibration of the molecules at equilibrium position. So vibration of the molecules are responsible for the heat conduction. In metals, the heat conduction occurs primarily due to the drift of the electron than the molecular vibration. And this is similar to the molecules in gas and referred as electron gas. So what we are trying to discuss here is, in metals, the heat conduction takes place primarily because of movement of the electrons, and this is similar to the movement of the molecules which we see in the gases. So this is also referred as electron gas when we are looking at the metals, the drift of the electron or drift of the free electrons is referred as the movement of the electron gas. Okay. So this is just an analogy with the kinetic theory of the gases and the conduction in the metals. And this is primarily the reason why the good electrical conductors are also good conductor of heat. So the materials having the higher electrical conductivity also possesses good thermal conductivity. So this is primarily because the heat is conducted by the movement of the electrons. Okay. So unlike the solids, in gaseous mediums, the conduction occurs through the collision of the molecules having more thermal energy with molecules having less thermal or kinetic energy. So how the heat is conducted in the gaseous medium? The molecules with higher kinetic energy collides with the molecules with lower kinetic energy, and by doing that they transfer their kinetic energy to the the less thermal or kinetic the molecules having less thermal or kinetic energy, and in this way the heat is exchanged between the molecules and eventually the heat is transferred from one location to the another. Okay. A similar thing occurs also in the liquid, but in liquid, in addition to this, there are some more the effects are also present. Okay. So is there any question so far? So let's move to the quantitative analysis of the conduction. So in order to quantify the conduction, the rule which is used is the law which is used is the Fourier's law of heat conduction. It states that if two plane parallel surfaces each having an area A is separated by a distance L and are maintained at temperature T1 and T2 respectively, the rate of heat conduction at steady state through the wall is given by this particular equation, where Q is the heat transferred in watts, and that is given as Ka. K is nothing but the heat conductivity, which is the unit is watt per meter per degree Celsius, into delta T. So delta T is nothing but T1 minus T2 divided by L. Okay. So here you can see, so there is a slab is there. There is a slab is there. The cross sectional area of the slab is A. The temperature at the left hand side of the slab is T1, which is higher. The temperature on the right hand side of the slab is T2, which is lower. So T1 is higher than T2, and the thickness of the slab is L. So heat is transferred from T1 to T2. So the rate of heat transfer or a amount of heat transfer, heat conduction through the slab is given as Q is equals to Ka T1 minus T2 divided by L. So this is nothing but the Fourier's law of heat conduction, which states that if two plane parallel surfaces each having a surface area A are separated by a distance L and are maintained at temperature T1 and T2, then the rate of heat conduction is proportional to the temperature difference and inversely proportional to the thickness. Okay, so here the K is the thermal conductivity of the solid and is assumed to be constant throughout the wall. Again, this Fourier's law of heat conduction is now given in a differential form. So in a differential form, Qx is equals to minus K dt by dx, where Qx is nothing but the heat flux, the rate of heat conduction per unit area, normal to the x direction, a direction of the heat transfer, is equals to the minus K into dt by dx. So minus, here minus sign is primarily because the heat is transferred from the higher to the lower temperature, and also here K is nothing but the thermal conductivity, which is given as watt per meter per degree Celsius, and dt by dx is nothing but the temperature gradient in the x direction, so from higher temperature to the lower temperature. So this is the differential form of the Fourier's law. Okay. So what we have seen so far in the Fourier's law is you can clearly see that the thermal conduct the heat flux is proportional to the temperature gradient, and the proportionality constant is K, where K is nothing but the thermal conductivity. So thermal conductivity, let's look at the thermal conductivity in detail. Thermal conductivity is a fundamental property like a viscosity, diffusivity. The thermal conductivity is a fundamental property. It gives a measure of the effectivity of the material in transmitting the heat through it. So basically it governs how good a material is a conductor of the heat, or how good a conductor of heat or not, that is governed by the property thermal conductivity. It also depends on the chemical constitution. It also depends on the characteristics of the material, whether the material is solid, liquid or gas. It also depends on whether the material is crystalline or amorphous, and also it depends on whether what physical conditions are present, like temperature and pressure. So depending on these factors, the thermal conductivity varies. So let's look at some more details of the thermal conductivity. So in crystalline material, the thermal conductivity is higher compared to the amorphous material because the vibration of the crystal lattice transmits the energy. So whenever we have the crystalline structure, that facilitates the easier transport of the heat energy, and therefore the thermal conductivity of the crystalline material is higher compared to the amorphous material. Again, thermal conductivity depends on the temperature. And if you look at the metals, the thermal conductivity of the metals generally decreases with the increase in temperature. So as we increase the temperature of the metal, its thermal conductivity increases. The exception here is the aluminum. Again, the thermal conductivity of metals decreases with impurity. So if the impurity increases, the thermal conductivity decreases, and pure metal has the highest thermal conductivity. So unlike the good conductor of the heat, there are some materials which are the poor conductor of the heat, and these materials are referred as the insulators. So solid substances having the low thermal conductivity, which are regularly used for reducing the rate of heat exchange, are called as thermal insulators. The common examples of thermal insulators are clay, bricks, zirconia, alumina, etc. Very often the insulating materials are like a foam like structures are there. For example, polyurethane foam is used as an insulator. So here you can see because of the foam, there is a gas, or there is a gas is entrapped in the voids present in the foam, and this gas basically is responsible for the insulating property. So high void volume fraction makes an insulator more effective. The presence of gas is more responsible for insulating property than the thermal conductivity of the material. So why the gas is responsible for the insulating property? Because the thermal conductivity of the gas is much lower compared to the thermal conductivity of the solid, and therefore if we use the foam like structure, even though the thermal conductivity of the actual material is not very low, but the effective thermal conductivity of the complete material, which involves the gas entrapped in the voids, becomes much lower. Okay. So is there any question? Some background noise is coming. Hello. 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 Can you mute everyone? Can you mute your mic? Balraj, your mic is on. Please mute your mic. Okay. 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 So the insulating materials are mostly like a foamy like materials where the effective thermal conductivity is lower because of the gas entrapped in the void, and since the thermal conductivity of gases is lower compared to the material, overall the thermal conductivity of the complete material is lower. Okay. The thermal conductivity of the insulating material increases with temperature. So thermal conductivity of the insulating material increases with the temperature. Okay. Now, unlike this, if you look at the liquid, for liquid the thermal conductivity decreases with temperature. The exceptions are the water and glycerin. So for water and glycerin, the thermal conductivity increases for a certain range of the temperature. Except this, the thermal conductivity of the liquids decreases with temperature. So this is similar to the viscosity. Remember, even viscosity of the liquids decreases with the increase in temperature. Again, except the liquid metals, water has the highest thermal conductivity. The last point is thermal conductivity of the gases increases with the temperature and decreases with the molecular weight. And again, among the gases, hydrogen has the highest thermal conductivity. Again, based on this concept, you can clearly see now why the thermal conductivity of the insulating material increases, because it is predominantly has the gases. And since the thermal conductivity of the gases increases with the temperature, sorry, I think thermal conductivity of the insulating material decreases with the temperature. Thermal conductivity of the insulating material decreases with the temperature. Let me check. Just wait. Let me just check thermal conductivity of the insulating material. We will check this whether thermal conductivity of the insulating material increases or decreases with temperature. Let me just check it later. Okay. Anyway, let's move to the next slide. Is there any question so far? Hello?
No, sir, no question.
No, sir.
Okay. Okay, so the typical range of thermal conductivity, if you look at, thermal conductivity of the solid is the highest, thermal conductivity of the liquid is lower than the solid, and gases has the lowest thermal conductivity. If you look at the typical values of the thermal conductivity of the silver is 410 watt per meter Kelvin. Thermal conductivity of water is around 0.63 watt per meter Kelvin, whereas the gases such as air has the thermal conductivity of 0.0262 watt per meter Kelvin. Okay. So here you can see as the state of the system changes from solid to gases, thermal conductivity, there is a significant change in the thermal conductivity takes place. In fact, there is a order of magnitude changes in the thermal conductivity. Okay. Again, so far we have seen that the thermal conductivity is constant, and in general thermal conductivity and average value of the thermal conductivity is used, but thermal conductivity is also a function linear or a quadratic function of temperature. So K is given as K naught 1 plus AT plus BT square. This equation is very important. Thermal conductivity is also a function of temperature. In most of the cases we use K equals to constant value, where this constant value is nothing but the averaged value, but it is also a function of temperature, linear or a quadratic function of temperature. Okay, where A and B are the constants. K naught is the thermal conductivity at absolute zero temperature. Again, the last point is thermal conductivity can also be a function of direction. It can varies along the direction. So if it varies along the direction, then the material is referred as anisotropic material. And if it is not varying along the direction, then it is referred as a isotropic material. Okay. If the thermal conductivity is same in all the direction, then the material is referred as isotropic material. If it is varying along the direction, then it is referred as anisotropic material. Okay. So this is all about the thermal conductivity. These are very, important questions. In fact, all these small questions are regularly asked in the GATE examination, isn't it? So what is the typical value of thermal conductivity of the water? What is the typical value of the thermal conductivity of silver? Or what is the thermal conductivity of air? These are, one should know the typical, range of the values for solid, liquid and gases. So for example, in solids, it will be in hundreds. For liquids, it will be in 0.1, around 1 or 2 in that range, isn't it? 0.63 is for water, isn't it? That is the highest for liquid, isn't it? And for air, it is 0.0262. So this order of magnitude, remember. Again, here, we are taking the exceptions of, liquid metals. Liquid metals like the mercury has the thermal conductivity in the range of 13,000. Okay. So liquid metals has very high thermal conductivity. Sorry, liquid metals will have a very high thermal conductivity than the water. Okay. So let's move to the conduction, the steady state conduction through the composite solid. So let us consider a composite wall consisting of 3 layers of materials, 1, 2 and 3. So here you can see there is a composite wall made up of 3 layers, layer 1, layer 2, layer 3. The thicknesses of these layers are L1, L2, L3. The temperature outside the left hand side of the layer 1 is T1 and the temperature on the right hand side of the layer 3 is T2 and the temperature at the interfaces interface of 1 and 2 is T dash and the temperature at the interface of 2 and 3 is T double dash. Again, the cross sectional area is common for all the 3 layers, which is equals to A. Now here, if you look at the resistance to heat transfer, these resistances to heat transfer are in series. So this is again shown in a network diagram like as shown here in the bottom. Here you can see on the left hand side there is a T1 and on the right hand side there is a T2. The intermediate temperatures are T dash and T double dash. The resistances in the first layer will be L1 by K1A. This we will see in the next slide. Similarly, the resistance in the second layer is going to be L2 by K2A and resistance in the third layer is going to be L3 by K3A. So here you can see in this particular example, in this composite solid system, so solid system of 3 layers, here you can see the at steady state, the heat transfer from through each of these layers Q1, Q2 and Q3, these are going to be same as Q because the area of the cross section is equal. Area of the cross section is constant and at steady state the same heat should be transferred from one layer to the another and from the second layer to the third layer because all these 3 layers are in series. So if the thermal conductivities of the layers are independent of the temperature, remember this can be the function of temperature, but if we assume that the thermal conductivities are independent of the temperatures, in that case the temperature profile, how the temperature is going to decrease along the layer will be a straight line. So unless if the variable area is there, or if the thermal conductivity is a function of temperature, in that case we get a curve here. Otherwise we will get only a straight line. Here you can see from T1 to T dash there is a straight line which is shown by a red colored line here. So there is a straight line I have shown. So there is a decrease in the temperature takes place in a linear manner. But if we have a thermal conductivity function of temperature, in that case we will have a non-linear curve. So we will instead of having a straight line, we will have a curved line here when the thermal conductivity is a function of temperature. So again from layer 2 we will have a straight line, and from layer 3 again we will have a straight line. So all 3 layers will have a straight line profile, but this will have a different slopes based on their thermal conductivities. So for layer 1, if we apply a Fourier law of heat conduction, so Q is given as thermal conductivity K1, which is nothing but the thermal conductivity of the layer 1 into cross sectional area A into temperature difference, that is going to be T1 minus T dash divided by the thickness of the layer, which is nothing but L1. So this is the first equation which we can rearrange. So T1 minus T dash can be obtained as Q into L1 by K1A. So here you can see in this particular equation, capital Q is given as K1A into delta T divided by L1. So here delta T is nothing but the temperature gradient or temperature difference, which is nothing but the driving force. Whereas L1 divided by K1A is nothing but the resistance. So that is what I have used here. L1 divided by K1A is nothing but the resistance in the layer 1. Similarly, in layer 2, capital Q can be given by a Fourier law of heat conduction, which is nothing but thermal conductivity into cross-sectional area into temperature difference divided by the thickness of the layer, isn't it? So here the temperature difference is going to be T dash minus T double dash and divided by the cross-sectional the thickness of the layer 2, which is nothing but L2. Again we can rearrange this equation. So T2 dash T double dash minus T dash, sorry, T dash minus T double dash is given as Q divided by L2 divided by K2A. Similarly for layer 3 we can write down the Fourier law of heat conduction, which can be given as K3A T double dash minus T2 divided by L3. Again we can rearrange this equation. By rearranging these two equations we can obtain T double dash minus T2 equals to Q L3 divided by K3A. So can you see my pointer here when I'm moving when I'm moving this pointer? Can you see the pointer here on the slide? Hello?
Sir, where it is right now, it's not showing up, I guess. Could you please show again? Here, now it is visible. It is.
It is visible. Okay. So the pointer is moving. Okay, good. Okay. So, so from these three equations, we have obtained the temperature difference for layer 1, layer 2, layer 3, and all these temperature differences we can add. By adding all these temperature differences, we get the overall temperature difference or overall temperature driving force, which is nothing but T1 minus T2. So by adding these three equations, T1 minus T2 is obtained as Q in the bracket L1 by K1A plus L2 by K2A plus L3 by K3A. So this bracket term is nothing but the total resistance. Again we can rearrange this equation. So Q, which is nothing but the net heat transfer in watt, is given as delta T, which is nothing but T1 minus T2, that is nothing but the driving force, divided by the total resistances. So here L1 by K1A is nothing but the resistance R1, L2 by K2A is nothing but the resistance R2, and similarly L3 by K3A is nothing but the resistance R3, and all three resistances are added in series. Here you can see all three resistances are in series. So rate of heat transfer here is obtained as temperature driving force divided by thermal resistance, and this is similar to the electrical conductor. So in electrical conductor, current is also given as the potential difference divided by electrical resistance. So there is an analogy between the electrical conductor and the thermal conductor. Okay. So thermal resistance in layer 1 R1 is going to be L1 divided by K1A. Thermal resistance in layer 2 is nothing but L2 divided by K2A. And similarly, the thermal resistance in layer 3 is going to be R3, which is nothing but L3 divided by K3A. And all three resistances are additive, and these are added, which is given as temperature difference divided by Q, where Q is nothing but the net heat transfer. So thermal resistance is additive, similar to the electrical resistances in series. Okay. Okay. So now based on this, let us solve one example to understand the conduction through the steady state conduction through the composite solid. Okay. So what is been given here is the wall of the cold storage consists of three layers, an outer layer of ordinary bricks. Then the middle layer is 25, outer layer is the ordinary bricks. The thickness of the ordinary bricks layer is 25 centimeter. Then there is a middle layer of cork. The thickness of the middle layer is 10 centimeter. And then there is a inner layer of cement which has the thickness of 6 cm. Again, the thermal conductivities of the materials are given. The brick is 0.7, cork is 0.043, and the cement is 0.72 watt per meter degree Celsius. So these are the thermal conductivities of brick, cork, and cement. The temperature of the wall is 30 degrees Celsius, and that of the inner layer is minus 50 degrees Celsius. So here you can see this three insulating layers are applied in order to maintain the temperature of minus 50 degrees Celsius, and the outside temperature is the ambient temperature around 30 degrees Celsius. So we wanted to minimize the heat transfer from the refrigerated area, which is at minus 50 degrees Celsius, to the heat transfer to the ambient, which is at 30 degrees Celsius. So what we have to calculate here is the steady state rate of heat gain per unit area of the wall, the temperature at the interfaces of the composite wall, and last we are interested in the percentage of the total heat transfer resistance offered by the individual layers. Again what is been asked is if the rate of heat transfer has to be decreased by 30% than the present value, how much the thickness of the cork layer should be increased. That is what the second part of the question. Okay. Now what is been given here is the thickness of individual layers are given, outer temperatures and the inner temperature, outer and inner temperatures are given. The thermal conductivity of all three layers are given. So now based on that we can find out the resistances of the individual layers. So brick layer resistance R1 will be given as L1 divided by K1A. L1 is nothing but 25 centimeters, so that becomes 0.25 divided by K1 is nothing but 0.7 into area here. Remember here per unit area is asked, isn't it? Is a steady state rate of heat gain per unit area. So area is assumed to be equals to 1 meter square. So the resistance R1 is calculated as 0.25 divided by 0.7, and that comes out to be 0.357 degrees Celsius per watt. Similarly, the resistance offered by the cork layer R2, the thermal resistance offered by the cork layer R2 is calculated as L2 divided by K2A. We can put all the values here. So the thickness of the cork layer is 10 centimeters, so that becomes 0.1 divided by 0.043. So 0.043 is the thermal conductivity of the cork layer. So based on this, the resistance R2 comes out to be 2.326 degrees Celsius per unit per watt. Similarly, the resistance offered by a cement layer is given as R3, and again the R3 is obtained as L3 divided by, again R3 is obtained by L3 divided by K3A. So here the thickness of the cement layer is 0.06 divided by the thermal conductivity of the cement layer, which is 0.72 into area 1, and that becomes 0.083 degree centigrade per unit watt. So these are the resistances offered by individual layers. Remember, what is the rate of heat transfer? The rate of heat transfer is nothing but the driving force divided by total resistance. So we have to first find out the total resistance. So these individual resistances are added to obtain the total thermal resistance. So total thermal resistance RT is nothing but R1, R2, R3. That comes out to be 0.357 plus 2.326 plus 0.083, and that comes out to be that comes out to be 2.766 degrees Celsius per watt. Okay, so now this total thermal resistance is nothing but what? Total thermal resistance is nothing but what? Total temperature gradient divided by Q. So we can back calculate the value of Q. So Q can be obtained as here delta T is what? Delta T is nothing but 30 degrees Celsius is the ambient temperature, and the inner wall temperature is -50. So the total temperature difference in this case is 30 minus -50. So that becomes 45. So Q is nothing but 45 divided by the total resistance, which is nothing but 2.766. So that comes out to be 16.27 watt. So the rate of heat gain by the wall is nothing but 16.27 watt. Now, the second part of the question was we have to find out the temperature at the interfaces of the composite wall. So that means we have to find out T dash and T double dash here. So again, let's look at the temperature drop across the brick layer. So temperature drop across the brick layer is nothing but T1 minus T dash, where T dash is the interface between the brick layer and the cork layer. So that is given as Q into L1 divided by K1A. So Q we already know, the total heat transfer we already calculated, that is 16.27. So this total heat transfer 16.27 we can put it here into the resistance of the first layer, which is nothing but 0.357. So T1 minus T dash comes out to be 5.8, and since T1 is 30 degrees Celsius, we can back calculate the T dash. So T dash comes out to be 24.2 degrees Celsius. Similarly, now we can look at the temperature drop across the cork layer. So for cork layer, the temperature difference is given as T dash minus T double dash, and that is given as Q into the resistance of the second layer. So that is nothing but L2 divided by K2 into A. So Q we already know 16.27. L2 by K2A, this resistance we have already calculated in the earlier slide, that is nothing but 2.326. So we can put it 2.326 here. So we get T dash minus T double dash as 37.8 degrees Celsius. Here T dash we already know, that we have already calculated. T dash is nothing but 24.2 degrees Celsius. So we can put it 24.2 degrees Celsius here, and we can calculate T double dash. So T double dash comes out to be minus 13.6. So the interface temperatures T dash and T double dash are nothing but 24.2 degrees Celsius and minus 13.6 degrees Celsius respectively. In part C, we have to calculate the percentage resistance offered by individual layers. So the layer 1, the resistance comes out to be 0.357, that is the individual resistance divided by total resistance, that is 2.766 into 100. So that comes out to be 12.9%. Similarly, the resistance offered by the cork layer comes out to be 84.1%, and the percentage resistance offered by cement layer comes out to be 3%. So here you can see the cork, which is nothing but the insulating material, is put between a brick layer and the cement layer in order to have a better, less, heat loss. In order to have the less heat loss. Now we wanted to reduce the heat loss by again 30%. In the second part, we wanted to reduce the heat loss by 30%. That means the total heat loss will be 16.27 into 0.7. So that becomes 11.39. So if you wanted to have 11.39 watt as a desired rate of heat flow, in that case, how much the resistance should be increased, that we can calculate directly. So this the required thermal resistance can be obtained as total driving force divided by rate of heat flow. So 45 divided by 11.39, so that comes out to be 3.95. So now the required thermal resistance should be 3.95 instead of earlier resistance was 2.766, isn't it? Now we require a higher amount of resistance, that is nothing but 3.95, in order to reduce the heat flow by 30%. So this additional resistance, the additional resistance is nothing but 3.95 minus 2.766. So that is nothing but 1.184. This is the additional resistance which we need to provide through a cork layer which is in between. So we wanted to increase the thickness of the cork layer so that this additional resistance will be provided by the cork layer in order to reduce the heat loss by 30%. So now the additional thickness of the cork layer, this resistance we know, so resistance is given as L2 divided by K2A. So K2A we can multiply to this resistance, so 1.184 into 0.043, that is the thermal conductivity of the cork layer, into 1, which is nothing but the cross sectional area. So this is nothing but 5.1 centimeter. So the thickness of the cork layer should be increased by 5.1 centimeter, which is now at the present it is 10 centimeter. Remember, the cork layer thickness is 10 centimeter. If I increase the cork layer thickness to 15.1 centimeter, in that case I will have a 30% reduction in the heat loss from the heat gain by the wall. Heat gain by the wall. So heat gain by the wall, if we wanted to reduce by 30%, the cork layer thickness has to be increased by 5.1 centimeter above the actual thickness of 10 centimeter. So this is all about the today's class. We stop here unless you have any question. We stop here unless you have any question. Is there any question?
No, sir.
Sir, can you explain again how Q is same?
How Q is
All
same? Yes.
yeah.
Let me just go. Okay. Okay. So why Q is going to be same? Remember, what is being said here is steady state. This word steady state is important. So that means what? The heat is transferred from layer 1 should be same as the heat transfer to the layer 2 and layer 3, because it's steady state, isn't it? And the heat transfer area is same. The transfer area is same. That is why the Q should be same in layer 1, layer 2, layer 3. So there is no accumulation, isn't it? There is no accumulation, there is no generation. Did you get it?
Yes, sir.
If there is a accumulation or generation, then Q could be different in these 3 layers. Otherwise, in steady state, the Q will be same. Any more question?
Sir, there was a small doubt regarding the tutorial timings. Can I discuss it?
Yes, please go ahead.
Sir, actually, we discussed with the other branch that is taking the course with us. It's a course for biotech as well as chemical branch. So they have their 1 to 2 wala slot fixed for certain days because of another tute. So as per the institute timetable, can we have it for from 2 to 3 on Monday and Tuesday?
2 to 3 on Monday and Tuesday. I said one will be on Monday and one will be on Thursday.
So because on Thursday we have one for this thermodynamics, no? So we wanted to condense 251 for Monday and Tuesday, if that's possible for 2 to 3.
Monday and Tuesday.
Monday group 1 and 3 and Tuesday group 2 and 4.
Okay. 2 to 3 you are saying?
Yes, sir. 2 to 3, Monday and Tuesday.
Okay, no problem.
Thank you so much, sir.
Monday and Tuesday, can we have it on some other day? Tuesday I am somehow, this Tuesday I will be little bit busy, but okay, Monday and Tuesday it's okay. Chalo, perfect, no problem.
Yes, sir. We wanted to have the slots as well as the days condensed, no, so that we can keep a regular touch with the other batch students too.
No problem. Monday and Tuesday we will have a tutorial for Monday. We will have batch 1 and 3 and
Yes, sir.
2 and 4 on Tuesday.
Yes, sir. And timings 2 to 3.
2 to 3. Perfectly all right on MS Teams.
Yes, sir. Yes, sir. Definitely.
Okay. Okay. No problem.
Thank you so much, sir.
Thank you.
Okay. Any more questions? Any queries regarding anything? Please stop me in between if you have any doubt in between. Am I going too fast?
No, sir. It's perfectly all
fine.
right.
It's fine.
Okay. Okay.
No, sir, it's
Okay.
fine.
So we stop here and see you then on Monday. Okay.
Yes, sir.